So we have learned how to specify Boolean systems or digital systems, and we have learned how to implement it in many, many different ways. And now we want to talk about what will be the best way to implement it, which people call the function simplification or function optimization. The goal of function optimization is trying to find an equivalent function with the minimum number of literals. So for example, I have this function f on 3 variables x, y, z, and it is the sum of 4 terms. And from the definition, I can implement this function using basic logical gates. The inverters give me all these complements. And then this AND gate, 4 AND gates create these 4 terms. And then finally, the OR gate add them up together. However, I take a look at this, I see, okay, so these 4 terms, they can be paired up in red and green. So for example, in the green terms, these 2 terms, they share y prime, z prime, y prime, z prime. The difference here is the first term is x prime, the second term is x. So when we do x prime plus x, we know this is 1. So that means the 2 green terms is equivalent to y prime, z prime. And similarly, the first 2 red terms can also be simplified to yz prime. So now we have yz prime and y prime z prime. So applying the same strategy again, we know this is z prime. So what this simplification procedure means, this tells us that this function is equivalent to the complement of z, which means that I can implement the same thing by this part. Instead of getting f from here, I can get f from here. They're equivalent. So from here we see why people are doing simplifications. Because compared to these 2 designs, this one here uses far less hardware. And less hardware normally means lower power consumption, faster speed. And the bottom line is they implement the same functionality. So in some sense, we said this is a better design. And how do people do function simplifications? So over the past several decades, so there are a lot of CAD tools has been developed to do function simplifications. And the don't care conditions have played a central role in most of these tools. So now let's use a small example to see how don't cares can help us to simplify functions. So let's consider a design of a 3-bit encoder, which is going to assign a 2-bit code to each of the 3 different input combinations. And here is the truth table for this system. We see the 3 different input combinations are 0, 0, 1, 0, 1, 0, and 1, 0, 0. And their code will be 0, 1, 1, 0, and 1, 1. So one thing we realize is, so we have 3 bits, which means that there are a total of 2 to the power 3, 8 different combinations of input. But however, the system specified only 3. And what happens to the other 5 input combinations? They are the things we call don't care conditions, because the user doesn't care what will be the output in these 5 cases. So now we list a few implementations of this system. So the first one is the one I do the straightforward one. To implement A, I see A is the sum of these 2 conditions. So A complements times Y times Z complements to make a 1. Plus the second situation, X times Y complements times Z complements. And if you want to simplify this a little bit, you see X prime Y plus XY prime, which means this will be true if and only if X and Y, they have different values, which is the definition of exclusive OR. And similarly, we can get the expression for B. So this is one solution. And however, we can have another solution here, which is much simpler here, using only 2 inverters. X is the complement of Z, and B is the complement of Y. And if you take a look up here, this does meet these two requirements. Whenever z is 1, a is 0. Whenever z is 0, whenever z is 0, a will be 1. And for b, it is the same. Whenever y is 0, b will be 1. Whenever y is 1, b will be 0. So this is a much better solution in some sense. And how we come up with this solution? What happens with other cases, other 5 don't care cases? So for these 5 don't care cases, because user doesn't care the outcome, so this code can be arbitrary because we don't care either. By using these don't cares in different ways, we can get actually a lot of other implementations. And later on, we're going to talk about the vulnerabilities behind all these better implementations, because they may not consider don't cares properly. So other than the don't cares that are missing from the truth table in the system specification, where else can we find don't cares? So this satisfiability don't care is one of the cases. So it is a part of the system where the input pattern will never occur. So let's see this small circuit here. We consider this NOR gate. By definition of the NOR gate, this is the truth table of NOR gate. And from this input here, we see the first input and the second input to the NOR gate, they are always complement to each other, which means that this case will not happen, this case will not happen. That also means that this output of the NOR gate, y, will always be 0. It can never be 1. So with this in mind, think about this exclusive OR gate. The y input cannot be 1, which means for the exclusive OR gate, the input combination x equal to 1, y equal to 1, or x equal to 0, y equal to 1 will never happen. And we represent these two cases by xy, which means x equal to 1, y equal to 1, and x prime y, which means x equal to 0, y equal to 1. So these are the two don't care conditions for this exclusive OR gate, because these two input combinations cannot be satisfied by the earlier part of the circuit. So that is why we call them satisfiability don't cares. So another source of don't cares is the one called observability don't cares. So this is the input combinations or the input patterns that will not affect the output. So let's think of this case. Y will be 0. When y is 0, this NAND gate will always give a 1, regardless of the value from this link. Which means that I don't really care what is the value here. I don't care the value here. As long as y is 0, this is always 1. The changes on this part will not be observed from outside. So in particular, in this case, when y is 0, no matter x is 0 or 1, I cannot observe the difference. So this is the one called observability don't cares, or ODC. So how this satisfiability don't care and observability don't cares can help us to simplify circuit. So consider the same example. By analysis, we know that it has SDC of x equal to 1, y equal to 1, x equal to 0, y equal to 1. And also by analyze the ODCs, we know there are two ODC conditions, x equal to 1, y equal to 0, and x equal to 0, y equal to 0. So now if you put all these four things together, these are all the input combinations of x and y. And they are all don't cares, which means that this logical gate is redundant. All the possible input combinations, they are don't cares. It is irrelevant to the output here, which in some sense, it means that we can ignore this gate, and then the circuit remains the same.